Hey, good afternoon, everyone.
Good afternoon, Professor.
How are you, Peter?
God bless you. God bless you.
Oh, thank you. How are you, Dexton? How are you? Um, so it looks like we have six people in here, and then let me check how many are in the. It looks like I have only five people. So one of you, right? Don't forget, one of you have forgotten to sign in on the sign-in sheet, right? So one of you have forgotten to sign into. If you are the one, please don't forget to sign in. Alrighty, so we're gonna have to pick up from where we left off last time, and which is basically finding the uh, solving for n, finding n, right? That's so. Let me. Where is this thing? Okay, I get rid of this and open a new one. So we all know, basically, we're dealing with four variables, right? Ah, P. First of all, let me put it. Right? So each time, right? Each time, if each of these variables are the unknowns, right? Right? Um, if future value is the unknown, we know it's p times 1 plus r raised to n, right? That's the very basic compounding formula, right? Okay, I want to, okay, make n look better. And then if, we've solved for each and every, right, variable, right, when they are the unknown. If principal is the unknown, right, of course, we will need to divide FV by, yeah. FV divided by 1 plus R to the N, right? All right. It's giving me such a headache. All right, I'll have to use the mouse. And if the R is the unknown, if the rate is the unknown, right, we know. Is the FV over P raised to 1 over N minus 1. Of course, in the second case, this is also called PV, present value, right? Now, finally, if N is the unknown, right, how many years will it take, right? So how do we solve for that? For that problem, we need to, now, think about it. We got to start, always, we need to start from the basic equation, right? The initial equation, and the initial equation is always what? Future value, the compounding equation, equals p times 1 plus 1 plus r raised to n. Now, our unknown this time is this n, right? I want to make a perfect circle. Okay, this is the unknown. But then, how do we isolate an exponent, right? How do we solve for an exponent? That's the big question. We cannot directly isolate it, so the first thing we will need to do is isolate whatever we can. I mean, if it is not n alone, but n is part of this, n is part of, exponent is part of that term, so then we will need to isolate this term first, right? Isolate this one first. How do we do that? Of course, we will need to divide both sides by p, right? Then the right-hand side will be isolated. 1 plus r raised to n. Okay, and then we know it is, it's basically, based everything I've been telling you over and over. All equations, no matter how complex it may look, key to solving any equations is to identify that z equals x times y structure, right? That format. X times y format. And if you did that, look, this is, exactly z, right? Right? X, right? P is x, and 1 plus r raised to n is y, right? So then, y is z divided by x. Or, to put it like this, I would, that if you divide z by x, then it will be y. But then, yeah, that's up to this, we're okay. Then the problem is, this is not z equals x times y structure, right? Because our unknown is n. Did somebody put something in the chat box? I need to. Okay, that was Eva. Good afternoon. Then, now let's think about it. The structure is rather more like this. The structure is like, rather, we got that, but if you think about it, this is more like, it's more like z equals x to the x raised to y, right? It's more like It's more like this, isn't it right? The structure is, look, this thing is z, right? This thing is x, right? I want a perfect, yeah. And this thing is y, right? Right? It's more like z equals x to the x raised to the y structure. So, so far we've been dealing with only multiplicative. We've been dealing with only multiplicative functions or multiplicative structure of equation, multiplicative, right? And then if it is multiplicative, simply, if this is the unknown of the multiplicative function, we can easily do that. But then now we are facing a totally different structure. It's, a power function, not multiplicative function, but power function, right? So in case of power function, if the exponent, the power, is the unknown, how do we solve for that, right? How do we solve for that? So how do we solve for the exponent, the power, right? And then to do that, the only way we can deal with it is by logarithm, right? By log. And what is a logarithm? Logarithm or log is a way of expressing a large number by the base and its exponent. Okay, so very well known, easy example. We all know, everyone knows, there are three types of logarithm, right? So let's take a look at it. There's common log, which is very, easy to understand. For example, 100 is 10 squared. 1000 is 10 cubed. 10,000 is 10 to the fourth, right? 10 to the fourth power. And these numbers, we can take log of these numbers to base 10. So log of 100 to base 10, you can read it either base 10 log of 100 or log of 100 to base 10, right? Then we can easily convert it, we can easily rewrite it as base 10 log of 10 squared, because 100 is 10 squared. And then when we have the base of the log and the base of the number same, when they are the same, the base of the log and the base of the number are the same, then what does that mean? That's 1. That means, it is 1. In other words, so I'll have to I can't, okay. I'll have to write it anyway. So in other words, 10 is 10 raised to 1. That means, it's just itself, right? And that would be expressed as base 10 log of 10 to 1. Of course, ignore that 1. So ignore that one, right? Think about it. It is already, what this means is base 10 log of 10, that's 1. It's just itself, right? And then 100, we know that's, 10, what's going on here? We know it is 10 squared. And if it is 10 squared, it can be written as log of 100 to base 10, which can be rewritten as base 10 log of 10 squared, base 10 log of 10 squared. And then an interesting, a very nice thing about log is these exponents can be brought down like the coefficient, right? So then it can be written as 2 times log of 10 to base 10. And what is this? This is 1. So it simply becomes 2. And also, the point is, this 2 means, that's squared, right? In other words, 100 can be simply expressed by 2, right? To the base of 10, because this 100 is, 10 squared. That's what it means, right? So anyway, because of this properties, right? Property of log, try, let's try even, what is it? Okay. We can extend it, like, even 1,000 or even 1,000,000. 1,000, we know it is 10 cubed, so it's base 10 log of 1,000, which is, base 10 log of, 10 cubed. Then it's going to be 3 times base 10 log of 10. Hey, this thing is 1 anyway, so it becomes 3. And then if we keep going on, we can already tell, if it is 1,000,000, right? If it is 1,000,000, if it is 1,000,000, log of 1,000,000 to base 10, that's, base 10 log of 10 to the 6th. So then it becomes 6. If it is 1,000,000,000, we all 9 zeros, right? 3 commas and 9 zeros. I really hate this. 1 billion, we know it's going to be base 10 log of 10 to the 9th power. So that will be 9. But then why do we express these numbers like that? Well, first of all, rather than expressing with a lot of zeros, it would be a lot easier to express it with exponent, right? 10 to the 9th, right? And then when we are dealing with very huge numbers, right? If you are dealing with very huge numbers, then it's going to be very difficult to manage. Why? Think about it. Suppose we want to reach the we want to go to the nearest galaxy, right? To our galaxy. Nearest galaxy to our galaxy is Andromeda galaxy, but it will still be like tens of light years away, tens of hundred, maybe not hundreds, but tens of light years away. And how far is a light year away? Of course, that's the distance the light travels a year. It will be billions of miles. It will be billions of miles at least, right? More than billions. So the point is then, how do we capture that enormous distance, right, on a piece of paper? I mean, how do we represent it? How do we represent that huge, enormous distance on a piece of paper? Or is there any way? I mean, even if I have a whiteboard that can be stretched, a physical whiteboard that can be stretched immensely, right? Maybe if I'm standing in the classroom at BMCC, the whiteboard I need would have to be stretchable. It must be stretched all the way from Lower Manhattan all the way to. I mean, if I stretch it westward, stretch it to the west, it will. I will need. It will need to go all the way to like Pennsylvania. In other words, suppose we are. Now, it's not such a far-fetched notion because all these billionaires, Jeff Bezos and Elon Musk, they all, are aiming to go to, Mars. Okay, they are aiming for this. There was a quote. I mean, on the internet, there was some tweet. Harry, William or Harry, the Prince of UK, commented, under Elon Musk's tweet. He commented, please save this planet, or what was that? What was his exact? Save this planet before, or rescue this planet before you go for another. But anyway, the thing is, if we are going to the nearest, right, not even Mars, but Andromeda galaxy, much farther away, way more. And then the distance between the Earth and the Andromeda galaxy, let's say we are comparing it to the distance between the Earth and the Sun. Okay, So let's say the distance between the Earth. Let's say this is the distance between the Earth and the Sun. Let's say this is the Sun. And let's say this is our green Earth. Actually, Earth looks blue from the space because of the ocean, you know. But you know, they say, you know, God's green Earth. Suppose that distance is, let's say, 10. Okay. Okay. And 10 doesn't mean, you know, 10 miles. It could be, you know, 10 million miles, right? But just, you know, that this, why is it just like this? Zero to one, let's say there's, you know, 10 million miles. Then between Earth and the Andromeda galaxy, right? The distance will be like, you know, how many times that, you know, let's say, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let's say, therefore, 21. And this is, you know, Galaxy A, Andromeda. And then now you might think, oh, the distance is only 21 times the distance between the Sun and it's only 21 times the distance between the Sun and the Earth. No, that's what it's. That if you think so, you are only used to normal scale. I mean, in normal scale, it looks like it's 21 times, right? Or 20 times. But if we use logarithmic scale, on logarithmic scale, 2 isn't 2 times. 2 is 100 times, right? In other words, we are using the exponents. So 2, that's like, you know, a log of 100, right, to base 10. So then it is, you know, 10 squared. That's 100 times. This is 10 cubed, right? 1,000 times, right? This is 10 to the 5th, 100,000 times. So then think about it. This will be 10 to the 10th. 10 to the 9th is billion. So 10 to the 10th will be 10 billion, right? Why is this so difficult? 10 to the 10th power. Yeah. And then, 10 to the 12th is trillion. 10 to the 12th is trillion, right? 10 to the 12th. And quintillion, right? 10 to the 15th is quintillion. You get the idea? 15 zeros. So if we use logarithmic scale, each notch is not double the previous one. Each notch is not, 10 times more the previous one, but it is actually, 100 times, 1,000 times, that way. So they are not same distance, right? The distance between this and this is not the same distance as between this and this, right? But this way we can manage, right? We can manage, a huge number. We can express a huge, number on a more manageable space, within a manageable space, right? That's one big benefit of using logarithm. But then we have, there are three types of logs, right? First of all, back to the reason we are dealing with, because we are using logs because of this property. The property of, what is the property? You see, when we take the log, we can think about it. This is originally a come on. This is a power function, but the power function turns into a multiplicative function, right? For this property, right? For this reason, because of this property, we need to use log. Why? Now let's get back to the this issue, right? So how do we then handle this? Z equals x raised to y, and y is the unknown. We want to find. We need to find y, and how do we do that? So think about it. If we take the log, it will be easily solved. Why? Because now think about it. Now, we want to take log, you have to take log on both sides, because whatever you do is an equation. And in an equation, whatever you do to one side, you have to do the same to the other side. But actually, what you wanted to initially you wanted to take log of the left hand or the right hand side, which is log of x raised to y. But then you have to do the same thing. You'll have to do the same thing to the left hand side, right? So I did it to the left hand side. I did it to the already did it to the right hand side. And then what does then what does it do? Now this can be the right hand side will be now y times log of x, right? Y times log of x. Then now, what is this now? It became now, this is the left-hand side. This is the right-hand side, and the right-hand side is now y times log of x. So in other words, what happened now? We have what used to be a power function, right? What used to be, this structure, z equals x raised to y. Now it is back to now it's back to z equals x times y structure, right? Or y times x. Then y is our unknown. So what do? All you need to do now is just like z equals x times y. If you know if x is the unknown, you divide z by y. Y is the unknown. What do? You will divide log of z by log of x, right? And what is then the question is, what is our z? What is our x? Our z is fv over p, right? And our x is 1 plus r. So then all we need to do is then, now we can solve this because now it is we know what's z and we know what's our x. So we take the log. We take the log of fv over p and divide it by log of 1 plus r. Okay? So this is how we do it. This is how we're gonna, but then next question. The problem is then, what kind of log can we use? In other words, can we use a common log? Can we use common log? And the common log is the log using 10 as the base. And there are largely three types of, there can be, the base of the log can be any number, but practically we use only about three types of logs. Common log, which uses 10 as the base. Binary log, which uses 2 as the base. If it uses the 2 as the base, then of course 4 is 2 squared. 8 is then log of 4 of log of 4 to base 2, or base to log of 4 is going to be 2. Log of 8 to base 2, or base to log of 8 will be 3. Base to log of 16 will be 4, and so on. And then there is, natural log. Natural log uses, Euler's number as the base. So here's the thing. What is the Euler's number? Now, let's think about it. The problem is, can we not use, common log here? Yes, you can, but it's gonna be kind of difficult. I mean, difficult to difficult to do the mental math. Why? Now think about it. If the base is 10, if the base is 10, it will be easy if this thing and this thing are all, some multiples of 4, right? You see what I'm talking about? If they are, or products, powers of 10, powers of 10. If this is, 100,000, then it will be 5, right? But obviously 1 plus r cannot be, something like that. So it's not impossible. I mean, the calculators will do that, but unless these numbers are like powers of 10, taking, common log will be a little, a little bit difficult, right? Binary log, that will be not that easy either, because, unless these numbers are, so we don't know what these numbers are going to be like, right? And these numbers can be, even continuously irrational number. What is an irrational number? So before I talk about that, so then the question is, what happened? Question is then, what is Euler's number? Because the question is, what is natural log? We'll take natural log, but in natural log, natural log is written this way. That's, ln. What would that n stand for? L stands for log, n stands for natural. Natural log of x, and natural log can take any number. It can take log of any number. But, natural log is the log using Euler's number E as the base. It's so sloppy and so messy. Using Euler's number E. So then, what is Euler's number? Now, it's not Euler. It's Euler, pronounced Euler. Euler was a Swiss-German mathematician, 18th century, 1700. There are two. If I can pick, two mathematicians that made a great impact to the modern world, modern, mathematics. Two German mathematicians, Euler, actually there are like three, Euler, Gauss, and Leibniz. Leibniz, they lived around the same time, around 18th century. So they are like probably a little after Newton, Isaac Newton. Isaac Newton was British, but he was, I think he was, 1700s. He lived in 1700s or 1600s, but pretty much, about the same time. I mean, prior to that, all mathematicians were like either, in ancient world, they were all, either Egyptian or Greek, right? Archimedes, Pythagoras, um, Pythagoras. Euclid, all ancient. But in a more recent time, like 18th century, Euler and Gauss, and then two major French mathematicians were like Lagrange and Fermat. Around 18th century, and during the Middle Ages, then a mathematician named Bachelier really made a big impact because the present day option pricing model is the based on the stochastic calculus, which is based on Bachelier's work. But the point is, okay, so then what is Euler's number? Euler's number is basically, a number that it's an irrational number. Irrational number means, it cannot have a fixed ratio. Okay, it cannot have fixed ratio. In other words, Euler's number is like 2.718, and it keeps on going, right? But then think about it. Irrational means oh, you're being irrational. Not that, but ratio. There's no ratio. There can be no exact ratio. Most of the numbers can have exact ratio, just like Euler's number is like pi. Pi is also an irrational number, right? Because it's 3.14 and it keeps on going. And then think about it. We can use, suppose 2/3, right? 2/3 is 66.67%. I mean, 0.66666. It keeps on going. 6 is repeating. You might say, oh, it suddenly, it suddenly turns to 70. No, it's just rounded. If you don't round it, if you let it go, it's going to be endlessly 0.6666666, right? However, it's still a rational number because it's the ratio is 2/3. That's the ratio. You can pinpoint the ratio. But a number like pi, they don't repeat, right? Euler's number, they don't repeat. It doesn't repeat. Numbers don't repeat. They are all different. So it's hard to nail an exact ratio, hence irrational number. So how did it come to be this number? So let's think about it. So we all know compounding frequency can be we have 1, annual compounding, 2, semi-annual compounding, 4, quarterly compounding, right? 12, monthly compounding. You can think of weekly compounding. Then there are 52 weeks in a year, but for all practical reasons, they don't use weekly compounding. Theoretically possible, but they don't use it. And then daily compounding. And then think about it. how far can we go? There can be, compounding by the hour, by the minute, by the second, and even by the nanosecond. In other words, but why? What is a nanosecond? Nanosecond is, nano is 9. Nano means 9. But you've probably heard of nanobots or nanites. What's a nanobot? Nanobot is a very, 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 very small, right, robot, right? They are one of the conspiracy theory about from the anti-vaxxers is such a ridiculous thing that in those vaccines there are microchips. Well, in other words, they are saying, there are nanites in the. Well, first of all, at the current technology, at the current technological level, we're still not there yet to have a small micro robot, right, nanite, that can pass through the needle. I mean, the diameter of the needle is still very, and we don't have the technology to build a robot on that microscopic level. But anyway, nano means, so nano is 9, but why does it mean such a small thing, microscopic thing? Because look, nano means 9, but what does that mean? So 9 seconds? No, nanosecond means 10 to the negative ninth of a second. 10 to the negative ninth of a second. What we know, negative exponent means, it's the reciprocal. So that is, give me a break. 1 over is 1 over 10 to the ninth. Right? That's what is nanosecond. Although, of course, it's only in theory. I mean, for all practical purposes, we don't even, we don't use that. For practical purposes, daily compounding is the maximum. But theoretically, it can go to infinity. Compounding frequency can go to infinity. Now think about it. Why would we pursue such, endless or infinite compounding frequency? Even for thought experiment, think about it. 1 year, we are breaking up 1 year, right? Okay, let me do this again. So you all recognize this. One plus APR over M raised to M. What does that mean? That's, basically we are and making adjustment. We are adjusting the annual rate by its compounding frequency, okay, per year. So per year there will be n times, right? There will be n compoundings per year, and let's just ignore. I mean, let's just for now assume that APR is 1. 1 means, it doesn't mean 1%, it means, 100%. Isn't that right? 1 is 100%. And the reason we do that is, because this one, we can easily replace it with actual APR later, right? We can replace it with actual annual rate later. But it makes our thought experiment easier. I mean, if the APR is 100%, that means every year it will double. Your investment will double. Isn't that right? 100% return means it will double. But then take this m. Let's take this m to infinity. Right? Infinite. We are infinitely splitting 1 year. Why do we do that? Well, think about it. If you are splitting up time by infinitesimal means infinitely small, right? Infinitesimal fragments, right? We can trace the continuity of time, fluidity of time. Now think about it. Time is actually a continuous thing, isn't that right? Time is a continuous thing. You understand what I'm talking about? Time is not a discrete thing. We cut up time into discrete units like year, month, quarters, right? Quarters, months, week, day, weeks, days, hours, minutes, seconds. But then these are discrete units of time. But if you think about it, time never existed in discrete units in the first place. Time, it's humans that came up with this discrete units. But time never declared, I'm minutes, I'm hour, right? Time never declared itself in those discrete units. Time flows continuously between 1 second to the next, right? You think, nothing is frozen, isn't it right? From 1 second to the next, nothing is frozen because time flows continuously. I mean, the second hand on the clock would tick from 1 second to the next. So for 1 second, that second hand is stationary, but then the next second it moves to the next notch, right? But that doesn't mean it's only because the clock works like that, but it doesn't mean the time is discrete like that. Time is, fluid, right? It's continuous and fluid. So if you want to replicate or capture that fluidity of time, I mean, if you want to express that fluidity of time, the only way we can do it is by cutting it up into infinite number of small fragments. And if you connect, think about it, all basically when we have discrete data, meaning let me use yeah. Oh no. Right. Let's say if we let's say over 20 years, let's say we are plotting the growth of the company revenue. I mean, if we use like 5-year time frame, let's say 20 years, that's fine. company's growth over 20 years, it will be, it will have a lot of kinks like that. But, because, the data collected were at every, right? Let's say we collected data every 5 years, or, every 4 years. But then if we collected data more frequently, like monthly, every month, or every day, then this whole graph will be more smooth, isn't that right? It will be smoother. It won't look like this. It will look more like. I'm sorry, that wasn't. It will look more like. Right? It will look more. It will look smoother like this. So that's the idea. If the reason we split time into infinitesimally small fragments is to capture the smooth fluidity and continuity of time. So the idea is, if we take this to infinity, in other words, then it's going to look like this. It's going to be now I can use the pen. One plus 1 over infinity raised to infinity. Now, here's the question. Here's your bonus question. Bonus point question. Now, when you divide 1 by, or any number by infinity, right? What's this number be? Anyone? When you divide any number by infinity, what's that number going to look like? Anybody? This is just logic. There is no calculation needed. I mean, because we don't have any number.
It's equal to 0.
Yeah. Peter, yeah, logically, but it's not, logically that's correct. But actually it's not exactly equal to 0. I mean, the only way you can get 0 is when you divide 0 by something, right? But when it will be close to 0. I mean, the correct way of saying that is it will be almost or close to 0, not equal to 0. Okay? It will be close to 0. Okay, Peter, so you got 0.25 for that. So then here's the thing. If this thing is exactly 0, the whole thing in the parenthesis will be just 1. Isn't that right? If this is 0, the whole thing is 1. And when you raise 1 to infinity, we have no problem. Raising 1 to anything will just be 1. Isn't that right? Because raise 1 to infinity, it will still be 1. 1 times 1 times 1 times 1 times 1 times infinitely times 1, still 1. Now here's then the question. Then we are at a little, we are at a little, what should I say? Mind-boggling point. Why? Is the thing, the parenthesis, the thing in the parenthesis, right? The thing in the parenthesis. Is it the thing in the parenthesis, right? Is it 1? No, it's not 1. It's slightly greater than 1. is slightly, I mean, insignificantly greater than 1. It's almost like 1.0000000000000 infinitely 0 and 1. And when you raise something like that, when you raise it to infinity, what's it going to be like? When you raise it to infinity, what's that number going to be like? Anyone? No idea. Okay, I know. If you raise it to infinity, right, a number that is slightly greater than 1, if you raise it to infinity, it becomes 2.718 and on and on and on and on and on. Irrational number. And this is called Euler's number, right? E. Euler's number, E. So why? Some people might say, it's greater than 1, still greater than 1. So wouldn't it be infinitely large number? You raise, it can be infinity if you are raising it to, if you're raising 1.5, for example, anything like even 1.01, 1.05, right? Even numbers like this, if you raise it to infinity, they will be infinitely large number. Anything greater than 1, you raise it to infinity, it will be infinity. But this is still greater than 1, but just insignificantly greater than 1. It's like almost no difference, but still greater than 1. Why? In other words, it doesn't grow infinitely, but it reaches some limit, right? It approaches and centers around a number like this. Why? Let me give you, let's do some experimentation here. You see, ignore these, ignore this, but just pay attention to this. And if interest rate is 1, right? I mean 100%, right? Not 6. Ignore this 6%. If interest rate is 100%, you see this is 1 plus 1 over m raised to m. This is the compounding factor, right? Compounding factor. And then when m is 1, it will be 2, right? Because it will double, right? If it is 2, 2.25, 4, but 365, 2.71, and then even 1,000, 10,000, even 1,000, it is still around 2.717, right? And then from about 10,000, the number doesn't grow that much. It's still just centers around 2.718, 2.718. I mean, between 10,000 and, look at this, 10 million. 10,000, between 10,000 and 10 million, it is, between 10,000 and 10 million, it's 1,000 times difference, right? There are 3 zeros and, yeah, 4 zeros. So even if the compounding frequency is 1,000 times this, still in this limiting case, right? I mean, it reaches some limit, which is centered around 2.71828. I mean, and this number keeps going. There is nothing repeating. I mean, the numbers are not repeating. These digits are not repeating. I mean, but they are centering around. They center around 2.71828. And even if you raise it to infinity, it won't be much different. If I raise it to infinity, it's something like this. So this number, that's an interesting thing. And that number is called Euler's number, and it is the basis of, it's the base of all natural logarithm. And the reason we use natural logarithm is because natural log doesn't, it doesn't have limitations in the numbers that it can take the log of. As I said, common log, powers of 10. I mean, it doesn't have to be, but it's not easy to visualize it, do the mental math. Anyway, it's not easy to do the mental math with Euler's number. But the point is, another thing is, it can take anything as, it can be the base of any power, because it is the number that is slightly greater than 1. 1 cannot be the base of any log, because think about it, 1 raised to anything is still 1. So it cannot be the basis of anything, any base of the log of any number, but something that is slightly greater than 1, if it is the basis of the base of the log, then and another reason is that it can take any it's a continuous it captures the continuous time. So any frequency, there can be no greater frequency than infinity, right? So it can be the base for log, base of the log for any number. That's why we use, natural log. Now, that is the explanation for why we use the natural log. In other words, to solve this problem, the mathematical foundation for why we use the log is this, the properties of the log. Then what kind of log do we take? We take natural log, okay? Natural log of the thing in the bracket. Okay? All right. So next time, next Tuesday, we can do the actual Excel exercise of Excel examples of this. Okay? So, all righty. So that's it for today. We're out of time. So I will see you guys on next Tuesday. Have a great afternoon and great weekend.
God bless, Professor.
All right, you too, Peter. All right, I'll stop sharing, stop recording, and sign out. So take care, everyone.